In the previous two videos, we discussed the distance time graph and the velocity time graph. In this video, we'll actually learn how to convert a distance time graph into a velocity time graph. So it is pretty simple. You just need to focus how we actually interpret the information from one graph and then transform that information into another graph. So let's actually draw a distance time graph first. So this is a ST. This is an ST graph, right? So this is an ST graph, and this is a VT graph, right? So I won't be actually scaling in and taking it into a numerically explicit video. I will actually be talking generically about the shape or the sketch of the curve, right? So or the graphs, right? So first of all, let's say that the car was initially at rest position, right? A car was initially at rest position, so we can have a point right starting from this origin, right? And then we can see that the car starts to move, right? So it is covering some distance with respect to time. And then let's say it stays at zero. It stays at it stays at rest position. The distance isn't being covered anymore, right? So the time is passing, but the distance isn't being covered, right? And once again, we see the distance being covered, right? And then after some time, it stays at rest, and then uh, we see, okay, we can see that it stays at rest at that point. We can keep it as simple, right? So let's actually convert this journey into a velocity time graph. How we can actually uh, transform the same information into a velocity time graph. So first of all, we can observe that the car actually started from initially a rest position. So the velocity was initially zero. So we can have the line starting from a rest position. Then we can see that the car starts to move. But since this is a straight line, this gives us an idea that the velocity was actually constant. So it goes to it actually goes to a constant velocity. So the constant velocity would mean something like it actually has a fixed value, right? Fixed value. So it goes horizontally. So the car immediately, goes to a fixed velocity like this, right? And then what happens? Then it stays at rest position. It is not moving. When something is not moving, you can assume it to be having zero velocity. So the line actually goes back to zero and it stays there for some time. Then we can see the car again starts to move at a constant velocity. So once again, the constant velocity would mean that the car is, in velocity time graph, it has to be horizontal line. But the gradient of this line would actually tell us the velocity of the car. For example, the velocity here was 2 meters per second, right? And the velocity here, since it is a little bit more steep, it is steeper than the one here, so it is going to be 3 meters per second, let's say. So in this case, the velocity here, the line here that is horizontal would be representing the 2 meter per second, and let's say 3 meter per second mark is here. So in the next phase, the car is actually moving in this phase from this point to this point. It is 3 meters per second, so it will be actually moving at a constant velocity of 3 meters per second. And then it actually stays at rest. So this is rest position. This is also rest position. And in velocity time graph, the rest position means zero velocity. So the graph will go all the way down again and finish its journey like that. So this is a representation of the velocity time graph of the same journey of the car that was represented by the distance time graph. Now let's actually suppose that this did not happen in the end. The car actually moved back. The car actually moved back. In the distance time graph, moving back would mean, let me actually draw it here. So in the distance time graph, moving back would mean that the distance or displacement is covered negatively. So the car will actually come back down like this, right? But how do we represent the same thing in the velocity time graph? In velocity time graph, uh, we just need to find out the gradient. For example, it is coming back at the speed of 4 meters per second, right? So we will, since velocity is a vector quantity, we can, just incorporate the negative axis here, and then we just need to see where is 4 meters per second on the negative axis. And since we erased the portion of the car where it was staying at rest, so we know that at this point the car actually moves backwards at a speed of 4 meters per second. So we just need to go all the way down, and here we just need to tell that it is now going at a velocity of 4 meters per second. But in velocity time graph, as you move down to the negative axis, this is the negative y-axis, below this, x-axis, you can see that the car is actually moving backwards. So the negative axis in the velocity time graph represents the motion that is in backward direction. However, in the distance time graph, you never actually go down to the negative axis. Why is that? Because you actually never moved from behind the initial position. For example, the car actually starts its journey here, and then it goes all the way forward. It stops at some points where I'll just label the rest position, and then it goes back somehow. Like it did not actually cross the initial position. If it did actually cross its initial position, then the line would actually go down below the negative axis. That would mean uh, that the displacement is now negative. The car actually moved in the reverse direction from its original position. In the velocity time graph, you just need to go down the negative axis in order to represent that the motion of the car is now backwards. So this is how you can interpret or translate a distance time graph into a velocity time graph.